Next, we will discuss how to do calculus with the hyperbolic arctangent function. Let's consider the hyperbolic arctangent function and let's find its derivative. Of course, we can use the limit definition of the derivative, however, we get stuck quick. But let's not forget the alternative definition of the hyperbolic arctangent function. We can differentiate this function using the chain rule, which is particularly easy when applied to the natural logarithmic function. Simplifying the expression produces a surprisingly nice result. In summary, we now have the formula for the derivative of the hyperbolic arctangent function, as well as the formula for the antiderivative of its derivative. Let's, for example, find the derivative of the following function. We start the process by recognizing that we have to find the derivative of a composition of the hyperbolic arctangent function applied to the square function, which is equal to the following expression, in which we know how to find all the components. We get the final answer after plugging everything in and simplifying. Let's, for example, find the derivative of the following function. We start the process by recognizing that we have to find the derivative of a composition of the square root function applied to the hyperbolic arctangent function, which is equal to the following expression, in which we know how to find all the components. There isn't much to simplify here after plugging everything in. Let's do an example of an integral. We first recognize the pattern and rearrange the integrand. Then we set up the substitution by setting a new variable, let's say t, equal to the hyperbolic arctangent, and finding the differential of t. Next, we plug in everything into the original integral and notice how, because of the discovered pattern, we have nothing but the function of t left in the integral. We finish the process by finding the antiderivative and plugging the original function back for t. Let's do another example, this time of a linear substitution. We set up the linear substitution by setting t equal to 6x and finding the differential of t and expressing the x in terms of the t. As a result, we have a simple indefinite integral in terms of t. We continue with the integration process by finding the antiderivative and replacing t with the original function. We discussed how to differentiate and integrate the functions that have the hyperbolic arctangent as one of their components.